Upper Missouri Country, January 1840. The spirit thermometer nailed under Marcus Thompson's eave reads 15 degrees below zero, yet inside both his cabins, shirt sleeve temperatures hold steady at 67 degrees. One fire, two separate buildings. Thompson had built something the other trappers called wasteful, a massive stone firebox centered between two cabins, connected by what he called a double-back flue system. His neighbors laughed at the elaborate masonry, insisting that two cabins needed two fireplaces. They dismissed his shared wall as too much stone, too much labor, too cautious for frontier life. Then the deep freeze hit. 3 nights of 18 below, steady winds, and the crisis that separated innovation from desperation. Standard log cabins with their corner fireplaces and stick chimneys failed catastrophically. Interiors dropped to 38 degrees despite burning wood all night. Smoke blew back in gusts, and families huddled under every blanket they owned. But Thompson's double-back system held both cabins at a comfortable 62 to 69 degrees, burning just 4 cords of wood for the entire season, while his neighbors consumed 9 to 10 cords each for their separate fires. What did this mountain man understand about thermal mass and controlled airflow that made the excessive preparation prove perfect when winter turned deadly? The norther that swept down from the Saskatchewan country in early December 1839 arrived with the merciless efficiency that separated experienced frontiersmen from dead ones. For 3 consecutive nights, the mercury plunged to 10 below zero and held there, while steady winds of 12 to 18 miles per hour drove the effective temperature far deeper into killing range. This was the weather that claimed lives through seemingly small mistakes: a poorly chinked wall, an inadequate fuel supply, or a chimney that failed when it was needed most. Hugh McKinnon's crew experienced the cascade of failures that defined standard frontier construction under extreme stress. Their cabins, built with 6 to 8 inch logs and mud chinking, featured corner fireplaces set 20 inches deep, with bark-lined stick chimneys that had seemed adequate during milder weather. The chimneys drew well enough in calm conditions, but the sustained wind created downdrafts that filled living spaces with smoke and forced the men to choose between suffocation and freezing. When McKinnon checked interior temperatures at dawn after the first night, his thermometer read 38 degrees despite wood having been fed to the fires throughout the dark hours. The physics of heat loss worked against every element of conventional construction. Thin log walls conducted cold directly into living spaces, while gaps in the chinking allowed wind to strip warmth as fast as fires could generate it. Corner fireplaces, positioned against exterior walls, lost much of their radiant energy to the outdoors rather than the interior. Most critically, the lightweight stick chimneys cracked under thermal stress, creating air leaks that destroyed draft efficiency and allowed precious heated air to escape. By the second night, McKinnon's men were burning wood faster than they could split it, yet interior temperatures continued falling. Wet mittens froze solid within hours of being brought inside. Bread dough failed to rise. Water buckets developed skin ice even when placed near the hearths. The gap between fuel consumption and heat retention had widened to a chasm that threatened to consume their entire winter wood supply before January arrived. Thompson's system operated under the same brutal conditions, but responded according to entirely different principles. The massive stone core had been designed to absorb and store thermal energy during active burning periods, then release that energy gradually across the hours when no fire burned. The morning routine began with carefully split fir and lodgepole pine, pieces cut to 14 to 16 inch lengths and 3 to 5 inches in diameter for consistent burning characteristics. The damper management required precision that separated effective operation from mere wood consumption. Thompson set the throat damper on the cabin A, side to 1/3 closed after ignition, creating just enough restriction to slow the gas flow without choking the fire. The cabin B damper opened in careful increments to draw combustion gases across the 36-inch lateral run through the stone mass. Most critically, the chimney plate required constant adjustment to maintain flue temperatures between 350 and 450 degrees, hot enough to prevent creosote buildup but controlled enough to maximize heat extraction from the passing gases. The thermal flywheel effect became most apparent during the overnight hours. While neighboring cabins lost heat steadily to the cold night air, Thompson's stone core continued radiating warmth at temperatures that kept both living spaces habitable. The cabinet face of the masonry maintained surface temperatures between 120 and 140 degrees for 6 to 8 hours after the evening fire died to coals. Cabin B received both direct radiant energy from its firebox opening and delayed radiant energy from the warmed stone mass, creating comfortable conditions through different but complementary mechanisms. Samuel Yates documented the quantified results with the precision his provisioning duties required. Thompson's cabins held steady temperatures between 66 and 69 degrees in Cabin A, 62 to 66 degrees in Cabin B, measured at floor level where cold air naturally accumulated. These readings represented a differential of 50 to 60 degrees warmer than the outdoor conditions, achieved with total daily burn times of 4 to 5 hours compared to the continuous feeding required in standard construction. The fuel efficiency proved equally dramatic, where McKinnon's crew consumed approximately 2 6/10 cords per month, operating 2 separate fireplaces. Thompson's combined consumption ran just 1 2/10 cords for both cabins. The difference represented not merely economy, but survival margin. The cushion between adequate preparation and catastrophic shortage when winter extended longer than expected or fuel supplies faced unexpected depletion. The labor savings compounded the fuel savings in ways that affected daily survival routines. Thompson made 1 to 2 fewer trips per day to the woodlot, a reduction that eliminated 40 minutes of exposure to killing wind and cold. Ash and ember management, typically a twice-daily chore for each fireplace, consolidated into a single routine that served both cabins. The time and energy saved translated directly into reserves that could be applied to other survival necessities, trap lines, gear maintenance, or simply the rest required to maintain decision-making capability under stress. The technical success attracted attention from unexpected quarters. Baron Daylight, visiting from the Knife River villages, examined the stonework and nodded approvingly at the thermal mass principles. The Hidatsa had employed similar concepts in their earth lodge construction for generations, using thick clay walls to store heat from central fires and release it gradually across long winter nights. The validation from Indigenous expertise carried weight that purely European engineering principles might have lacked. By the third night of the cold wave, McKinnon's men began appearing at Thompson's door, not as skeptics seeking to prove a point, but as survivors seeking refuge from systems that had failed when failure meant death. The double-back fireplace had passed its first severe test, but January would bring challenges that would push every system to its absolute limits. The cold wave that descended on the upper Missouri country in late January 1840 carried the signature of weather that killed without warning or mercy. For 5 consecutive days, daytime temperatures never climbed above 6 degrees below zero, while nights plunged to 30 and 35 below, conditions that froze mercury solid and turned human breath into ice crystals that tinkled when they hit the ground. The creek iced to depths of 10 to 12 inches, thick enough to support loaded sledges. Water barrels in standard cabins froze into solid blocks that required axes to break apart for melting. The failure cascade in conventional construction accelerated beyond mere discomfort into genuine crisis. Thin chimneys, stressed by repeated heating and cooling cycles, developed hairline cracks that widened into gaps large enough to pass a knife blade. The differential between interior heat and exterior cold created thermal expansion that pulled apart mortar joints and opened air passages that destroyed draft efficiency. McKinnon's men woke to interior temperatures of 24 to 32 degrees despite maintaining fires through the night, readings that represented the narrow margin between shelter and exposure death. Frost accumulated on interior surfaces in patterns that revealed the physics of heat loss. Iron nails and rafter ends, acting as thermal bridges between interior and exterior air, collected ice formations that grew throughout the night. Wet clothing hung near fires never dried completely, instead developing ice shells that cracked when handled. The men slept in full winter clothing under every available blanket, yet still woke stiff with cold that required minutes of movement to restore normal circulation. Thompson recognized that the extreme conditions demanded operational changes that pushed his system to maximum sustainable output. The standard morning and evening burn schedule required modification to maintain core temperature above the critical threshold where thermal mass storage became effective. He extended the morning fire to 3 hours of steady feeding with carefully sized splits, building heat gradually to avoid thermal shock that could crack the stone joints. The evening burn stretched to 2 hours, with particular attention to achieving complete combustion that loaded the core with maximum thermal energy. The key measurement became the surface temperature of the stone core itself, which Thompson monitored by holding his bare hand 6 inches from the masonry face. As long as the stones maintained what he called hand-warm temperature, roughly 100 to 120 degrees, the radiant heat release would continue through the overnight hours. This technique, learned from Baron Daylight's Earth Lodge practices, provided a reliable gauge of thermal storage without requiring instruments that might freeze or break. The extended firing schedule consumed approximately 1/3 cord of mixed Douglas fir and lodgepole pine over the 5-day period, with splits maintained at 14 to 16-inch lengths and 3 to 5-inch thickness for optimal burning characteristics. The wood selection proved critical under extreme conditions. Dry lodgepole caught quickly and burned hot enough to raise core temperature rapidly, while dense fir provided the sustained heat release necessary to charge the thermal mass fully. Interior conditions validated the system's performance under maximum stress. Floor-level temperatures at 4 in the morning, when radiant heat loss peaked and outdoor cold penetrated most effectively, held steady at 62 to 65 degrees in both cabins. Cooking water remained liquid overnight, allowing normal meal preparation without the time-consuming process of ice melting that plagued neighboring shelters. Bread sponge placed near the masonry face continued rising throughout the night, indicating that biological processes requiring stable warmth could proceed normally even in killing cold. The physics underlying the superior performance involved principles that frontier builders rarely understood but could observe in practice. Radiant heat transfer allowed human bodies to feel comfortable at air temperatures several degrees lower than would be tolerable near cold walls. A person sitting 6 feet from Thompson's stone core, radiating at 120 to 140 degrees, experienced thermal comfort at 62-degree air temperature that exceeded the sensation of 68-degree air in a cabin with cold wall surfaces. The extended gas path through the 36-inch lateral run functioned as a heat exchanger that extracted thermal energy from combustion gases before they escaped up the chimney. Standard corner fireplaces allowed hot gases to rush directly up short flues, carrying away energy that could have been captured in thermal mass. Thompson's design forced the gases to scrub against heated stone surfaces, transferring energy through conduction and convection that was then stored and released gradually. The safety protocols required constant attention under extreme conditions. Ash removal became a daily necessity rather than the every 3 to 4 day routine sufficient in milder weather. The increased fuel consumption filled the firebox floor with residue that could restrict airflow and create hot spots capable of cracking the stone work. Thompson developed a technique using a long-handled iron shovel to rake coals forward while removing ash through the clean-out door at the base of the lateral run. Creosote management took on critical importance as extended burn times increased the risk of glazed deposits in the flue system. Thompson maintained flue temperatures high enough to prevent condensation. The spit sizzle test on metal surfaces indicated proper heat levels, while avoiding the excessive temperatures that could ignite accumulated deposits. The balance required constant adjustment of damper settings as outdoor wind conditions changed throughout each day. The extreme cold attracted refugees from failed systems throughout the drainage. 2 families with children appeared at Thompson's door during the worst night, their own cabins having become uninhabitable when chimney failures filled living spaces with smoke. The cabin B floor accommodated the additional bodies, and wet gear that would have required 2 to 3 days to dry in standard conditions achieved complete dryness overnight near the radiating stone mass. The children's recovery provided the most dramatic evidence of the system's effectiveness. Feet that had appeared dangerously pale from cold exposure pinked up within 15 minutes of proximity to the masonry face. No one suffered the smoke-induced headaches that plagued occupants of poorly drafted shelters, and sleep came naturally rather than the fitful rest that characterized survival in marginal conditions. When the cold wave finally broke after 5 days, Thompson's system had demonstrated that proper thermal engineering could maintain not just survival, but genuine comfort under conditions that killed the unprepared and tormented the inadequately housed. The transformation in community attitude toward Thompson's system began not with dramatic pronouncements, but with practical requests that revealed the depth of standard construction failures. Hugh McKinnon appeared at the cabin door on a February morning, not seeking temporary refuge, but requesting detailed measurements and construction specifications. The same man who had dismissed the shared masonry as wasteful now carried a folded piece of bark paper covered with sketched dimensions and notes about foundation depths. Word of the successful winter performance had traveled the network of trading posts and winter camps, with the efficiency that characterized frontier information vital to survival. Visitors arrived throughout the late winter months, ostensibly on other business, but inevitably steering conversations toward heating systems and fuel consumption. Samuel Yates documented the inquiries in his ledger, noting requests for stone quantities, mortar recipes, and damper specifications from camps as distant as the Yellowstone confluence. The first replication attempt took shape during the spring of 1841, when the McCrae family, arriving from Illinois with limited seasoned timber, chose to build their homestead using Thompson's proven design. Sarah and Thomas McCrae had heard accounts of the system's performance through correspondence networks that connected frontier communities, and they possessed the crucial advantage of deliberate planning rather than desperate improvisation. Their site preparation began with careful selection of stone from a nearby creek bed, gathering river-rounded rocks that would bond effectively with clay sand mortar. The McCrae construction followed Thompson's specifications with modifications dictated by available materials and family needs. The foundation trench reached 12 to 14 inches deep, exceeding Thompson's original depth to accommodate the additional load of a slightly larger core. The base course measured 24 inches thick, rising to support a firebox system designed to serve a living cabin and a separate workroom where grain storage and tool maintenance required protection from freezing. Johann Kappel, now working regularly along the Missouri drainage, provided direct technical assistance to ensure proper proportions and construction sequence. The firebox openings maintained the 28 by 22 by 18-inch dimensions that had proven effective, while the throat construction incorporated the 7-inch restriction and 6-inch smoke shelf that controlled draft and prevented downdrafts. The lateral flue run extended slightly longer than Thompson's original, approximately 42 inches, to accommodate the increased distance between the McCrae buildings. The curing process required patience that tested the family's commitment to the unfamiliar technology. Following Thompson's documented procedure, they maintained low fires for 48 continuous hours, gradually raising temperatures to prevent thermal shock that could crack the stone joints. The clay sand mortar, mixed in precise 3-to-1 ratios, required time to achieve full strength through slow moisture evaporation rather than rapid heating. Sarah McCrae applied lime milk whitewash to the finished surfaces, creating a coating that would reveal hairline cracks early enough for preventive maintenance. The McCrae system's first winter performance validated the reproducibility of Thompson's design principles. Operating costs tracked closely to the original 3 8/10 to 4 5/10 cords for both buildings combined, compared to estimated requirements of 8 to 9 cords for separate heating systems. Interior temperatures remained stable at 60 to 66 degrees during sustained periods when outdoor readings dropped to 10 below zero. Most significantly, the family reported none of the smoke incidents that plagued conventional chimneys during windstorms. The success attracted attention from institutional builders facing heating challenges that exceeded domestic scale. Etienne Gervais, managing a 6-man bunkhouse and adjacent cookhouse for a trapping operation on the Musselshell River, commissioned a modified version that incorporated elements optimized for commercial cooking and group shelter. The shared core featured a 30-inch wide opening designed to accommodate cast iron griddles and large cooking vessels, while the flue system included a 2-stage gas path that added an additional 24 to 30 inches of heat extraction surface. The bunkhouse installation demonstrated the system's scalability beyond individual family applications. Gervais documented fuel consumption of approximately 4 cords per month for both buildings during peak winter conditions, representing roughly 50% savings compared to the previous season's separate heating systems. The consistent temperatures, 60 to 64 degrees, even at 10 below zero outside, eliminated the hot and cold cycles that had made sleep difficult and work uncomfortable in the poorly heated structures they replaced. The operational doctrine that emerged from multiple installations emphasized routine maintenance as the foundation of reliable performance. Ash removal schedules varied with fuel consumption rates, but generally required attention every 3 to 4 days during active heating periods. The clean outdoors that Pierre Laroche fabricated allowed access to accumulated debris without disturbing the firebox operation, while the damper systems required daily adjustment to match changing wind conditions and fuel characteristics. Sweep routines developed around 60-day intervals during heavy use periods, with particular attention to the horizontal flue sections, where creosote deposits could restrict airflow. The technique involved flexible brush systems that could navigate the lateral runs, removing accumulated residue before it hardened into glazed deposits capable of igniting. Thompson's original system required repointing of hairline cracks wider than 1/16 inch, a maintenance standard that prevented minor settling from developing into major structural problems. The humidity control benefits, initially observed but not quantified in Thompson's original installation, became apparent in the replicated systems. Interior moisture levels stabilized at 35 to 45% near the thermal mass, preventing the extreme dryness that caused log shrinkage and chinking failure in standard construction. The stable humidity also reduced respiratory irritation and improved sleep quality during the long winter months when families spent most of their time in enclosed spaces. By spring of 1842, at least 7 camps along the upper Missouri drainage had incorporated shared heating systems based on Thompson's principles. The variations reflected local materials and specific needs. Some included provisions for cooking, others featured enlarged thermal mass for extended heat storage, and several incorporated iron heating elements that utilized the warmed core as a heat source for auxiliary rooms. The fundamental concept had proven itself not as an isolated innovation, but as a replicable technology that addressed the universal frontier challenge of efficient heating in severe climates. The vindication of Thompson's thermal mass principles extended far beyond the Cottonwood Bend, where the original system had weathered its first brutal winter. By 1843, shared heating systems had become the preferred construction method for paired buildings throughout the upper Missouri drainage, with modifications that reflected the accumulated wisdom of multiple builders working under varying conditions. The technology had evolved from experimental innovation to proven doctrine, supported by quantified results that made economic sense even to the most conservative frontier builders. The documented performance metrics validated Thompson's original fuel consumption predictions, while revealing additional benefits that had emerged through extended operation. The McRae installation logged 3 5/10 cords for an entire heating season, maintaining comfortable temperatures in both their living cabin and workroom during a winter that saw sustained periods below zero. More significantly, the system eliminated the wood supply anxiety that plagued conventional construction. The gnawing uncertainty about whether split timber would last until spring thaw allowed resupply operations. Gervais' commercial installation demonstrated the scalability potential that attracted attention from trading post managers and military engineers. His 2-room complex, serving 6 men through a harsh Musselshell River winter, consumed 4 2/10 cords total, while maintaining working temperatures that allowed normal operations even during the coldest periods. The cost analysis revealed labor savings that compounded the fuel efficiency, fewer men needed for wood cutting and hauling, reduced maintenance time, and elimination of the constant fire tending that consumed productive hours in standard heated buildings. The technical refinements that emerged from multiple installations addressed operational challenges that hadn't appeared in Thompson's original single-user system. Pierre Laroche developed improved damper mechanisms that allowed more precise control over gas flow through the lateral runs, preventing the overdraft conditions that could waste heat or create dangerous temperature spikes. His fabrication techniques, refined through building hardware for 7 installations, standardized the ironwork dimensions that made the systems reliable rather than experimental. The regional adoption pattern followed the natural networks of frontier communication and seasonal migration. Trappers who had sheltered in Thompson's cabins during the 1840 cold wave carried detailed knowledge to their next assignments. Traders who had observed the fuel consumption advantages during provisioning stops began requesting similar systems at their permanent posts. Military engineers, always interested in efficient heating for frontier installations, documented the construction techniques and incorporated thermal mass principles into official building specifications. The broader influence reached beyond direct replication to inspire hybrid approaches that combined shared heating with other frontier innovations. Several builders incorporated stove thimble taps into their thermal mass cores, allowing iron heating devices to draw warmth from the stone structure even when no fire burned in the main firebox. This modification proved especially valuable in commercial settings where different rooms required heating at different times, or in family compounds where individual families wanted independent temperature control while still benefiting from shared thermal storage. The boarding house applications revealed the system's potential for urban frontier development. Establishments in growing settlements like Fort Benton and emerging mining camps found that shared cores could heat multiple rooms efficiently while reducing the fire hazards associated with numerous individual fireplaces. The liability advantages proved as important as the economic benefits. Fewer chimneys meant fewer potential ignition sources, while the massive stone cores provided inherent fire resistance that thin-walled conventional fireplaces couldn't match. The long-term durability studies conducted informally through Samuel Yates's ongoing documentation efforts showed maintenance requirements that compared favorably to standard construction. The stone cores required repointing every 3 to 4 years, but the joints held more securely than thin chimney mortar that froze and thawed repeatedly. The iron damper mechanisms needed replacement approximately every 7 years under heavy use, but the controlled draft systems prevented the thermal cycling that destroyed conventional flue hardware within 2 to 3 seasons. The knowledge transfer mechanisms that spread the technology reflected the informal education networks that characterized frontier technical development. Bear and Daylight's contributions became systematized into specific construction recommendations about clay sand ratios and thermal mass positioning that builders could follow without understanding the underlying physics. Johann Kappel's Old World masonry expertise translated into precise dimensional specifications that eliminated guesswork from throat sizing and smoke shelf construction. Thompson's operational experience converted into daily routines for damper management and maintenance scheduling that ensured reliable performance. The modern validation of Thompson's principles would eventually emerge through 20th century research into thermal mass heating and masonry heater technology. Engineers studying traditional European heating systems would rediscover the efficiency advantages of controlled gas paths through stone structures, while energy conservation specialists would quantify the fuel savings that frontier builders had achieved through practical necessity rather than theoretical understanding. The physics that Thompson and his contemporaries learned through trial and error would be confirmed by thermodynamic calculations that proved thermal flywheel effects and radiant heat transfer advantages. The cultural legacy extended beyond technical innovation to influence frontier attitudes toward resource conservation and systematic planning. Thompson's success demonstrated that what appeared to be excessive preparation during mild conditions proved exactly sufficient when extreme conditions arrived. This lesson resonated throughout frontier communities where the margin between adequate and inadequate preparation often determined survival outcomes. The willingness to invest extra labor and materials in thermal mass systems reflected a broader shift toward thinking systematically about winter heating rather than simply reacting to immediate cold. The geographic spread of shared heating systems eventually reached from the upper Missouri drainage through the northern Rockies and into the Pacific Northwest, carried by the migration patterns of trappers, traders, and settlers who had experienced the advantages firsthand. The technology adapted to local materials and climate conditions while maintaining the fundamental principles that Thompson had proven during that brutal winter of 1840. The legacy endured not as a monument to individual innovation, but as practical knowledge that continued saving fuel, labor, and lives wherever wood was scarce and winter was unforgiving.